All right, it's 4 o'clock. 4 o'clock. All right. Bit lighter on the attendance today. I think that might be. No, I guess maybe it was late. Why are you late? Okay, sit down. So some of you have now taken the exam. Exciting. Who here took the exam already? Last night. Thumbs up or thumbs down? Okay. Okay. All right, about 50-50. Okay. Cool. Well, best of luck to you. I think it'll be very similar to the main exam, but they are entirely different. Don't discuss them just for the sake of, don't give the others an unfair advantage. If you help them, it'll hurt you. So take that how you will. Yeah, did you guys end up using your cheat sheets a lot, by the way? A little bit. So okay. Interestingly enough, pretty much the exact same split. It was okay. Interesting. Okay, so today I'm going to do. So today's going to be a slightly more laid-back lecture. We are going to cover new content, and this content hypothetically could be on the exam. I think I will not. The two exams are balanced in difficulty, but do pay attention. The more important point of this lecture is that these are going to be algorithms that are not only optional but necessary for Project 2. So your current version of this, very likely those of you who have already finished your written portion, you say something at the end like, I construct this graph and I do maximum flow using Edmund Karp or Ford Fulkerson or whatever. And those are very likely not going to be fast enough to run on a computer in any feasible amount of time. It might take you a day or something to do a single image, and that will fail the grade scope test. You need to do them fast enough that grade scope, the grade scope runtime doesn't crash. Because it only stays open, I think, for like an hour or something like that. If it takes any longer than that, then you automatically fail the entire grade scope. Yeah. So yeah, grade scope does actually have a hard limit on how long you can run the code for before they just shut it down. And if you shut it down, it automatically fails all the tests. That's going to be the limiting factor. I don't actually know the number, by the way. This has been an issue in tests I've written in the past. So just know that can happen. Anyway, the algorithms today are going to be improvements on maximum flow, or perhaps empirical improvements, not necessarily asymptotic improvements. We're going to see how they work. So first up, Edmund Karp. Someone tell me, what's the main idea and what's its runtime? Sure, yeah. Okay, sure. Yeah. So we have Edmund Karp is going to be the better of the algorithms. Ford Fulkerson is take an arbitrary path. This marker is not very good. I'm going to get a new one. Edmund Karp is finding the shortest augmenting path. So we have this idea of an augmenting path, which is any path in the residual, and if we find the shortest one of those and apply them. Oh, was that actually mine? I guess mine got ruined. Okay, whatever. So Edmund Karp gives us a runtime. So this is just repeatedly take the shortest augmenting path, which is just going to be the first path found by BFS is guaranteed going to be the shortest path. And it gave us a runtime of O V E squared. Okay? And this runtime, could we decompose it into its components of how many times did we run our algorithm and how many iterations were in our algorithm and how much work was done by each one of those. So what was the number of iterations? What was it? It was V. So it was V. We went through a whole long proof to get to this number. It's OVE. I'm just going to write it as VE though. So this was basically the proof that by adding the shortest path, we will only ever have to do that this many times before we reach a maximum flow, which was derived through a whole bunch of lemmas and is not necessarily intuitive. Then we had the amount of runtime it takes for us to do our each iteration, and how much was that? So that was like a search for a path. It was E, yeah. So per iteration was it was V plus E, but we also realized that is O of E. All right, so that's just running something like BFS or GFS. They both take V of E, V plus E. Now, do you think that there's any way that we can improve on either of these? Which one do you think is more likely for us to be able to improve on? Yeah, you're sure. Okay, okay. Anyone else? Anyone have an argument that it might be the other one? Okay, okay. Well, let's hold that thought, and let's talk about the algorithm that if you Google search best maximum flow algorithm is very likely going to come up, but I will promise you is actually not the best empirical or asymptotic runtime one. So just a little bit of a little teaser of there's more things coming. But the algorithm that a lot of people, you'll see on LeetCode, this will be like the assumed LeetCode solution or something like that, is going to be Dinic, which is spelled D-I-N-I-C, which is, funnily enough, a misspelling of the guy's name. He's a Russian guy. The more accurate would be Kits, like that. But whatever, we'll use the bastardization Dinic's algorithm. Okay. So the core idea of Dinic's algorithm is based around two new definitions for us. So the first definition, I think I'll put the definitions over on this board just to make it easier. So the first definition is going to be a layered network. So we have a layered network. A layered network works like so. So in a layered network, we can have some arbitrary graph. Let's say I have some graph like so. So I have some edges that go forward to nodes. We have some that might go backwards like this. Something like this. Let's say we have some flow network like so. Okay. Now what we want to do is we want to make this easy to traverse, easy to find paths on. And it turns out that what we can do is we can just look at the forward edges. And what that means here is we're going to look at the distance, the minimum distance from S to every single node. So for example, the minimum distance from S to this node is what? 1. And how about to this node? 2. And then T we'll say is 3. And then this one will also be 1. But because there's another too long path here, it still is just 1 here. That doesn't shorten the length. And this one will also be 2. Okay? And what we're going to do is we're going to consider all of these groupings. So I've labeled all of them 1 and 2. We're not going to label them in practice, by the way, like in the implementation of this algorithm, but we can conceptually think about labeling them. I'm going to label this layer 1, label this layer 2, for example. And what we're going to do is we're only going to look at the edges that go from I'll call this layer 0 and call this layer 3, just for the, so this is layer 3, 2, 1, and 0. So what I'm going to do is I'm going to now construct a tree, which is just going to be the edges going from a lower layer to a higher layer. So if I were to draw this now, using just those edges, essentially what I would do is I would have both of these edges are going from 0 to 1, that's fine. But this edge that's now going from 1 to 1 will be removed. So we're not going to have that edge anymore. Okay? Similarly, when we go to the second layer, we're just going to have these edges now, like this, and we're going to also remove this edge here. Okay? So our final graph is just going to look like this. Okay? Does that make sense? This is what a layered network is. And you'll notice that it is a tree with the only intersection. I guess there could be intersections between these, but there's never going to be a backwards connection. There's not going to be any cycles. Okay? So, yeah, question.
How are you splitting up the
Distance from S. So it's a minimum distance from S, rather. Okay? So, this is going to be a layered network, and what we're going to end up doing, by the way, is making a layered network version of a residual graph. So we're all comfortable with residuals. I think we've talked about it enough. What we're going to be doing in this algorithm is we're going to be considering a layered network version of the residual. Okay? So I'll just put it in brief here that it's only take edges from lower layers, I'm calling that. That's distance to S. So lower layers, that means like distance from S. Lower layers to higher layers. And this will remove cycles. Okay? Cool. Everyone happy with that definition? It's more just a conceptual thing. Second definition is going to be a blocking or maximum or maximal flow. So blocking slash maximal flow. Does anyone have any sense of what the difference between maximal and maximum are, by the way? Any idea? Blocking here might give you a little hint as to what's happening with this. Any idea? Okay. So the basic idea of a blocking or maximal flow is that it's going to be a flow assignment such that there is no augmenting path. So I'll say something a little bit more specific that will not that there's no augmenting path. Something a little bit more specific that's made more helpful. Every path from S to T has at least one saturated edge. Okay. So every path from S to T has at least one saturated edge. Okay? So the way that we could get something like this, that is not necessarily maximum flow being the absolute maximum we could possibly reach, is if we took a single residual graph and then we found every possible path from S to T in it and applied all of them, then in that particular situation, there would no longer be any way that I could use this residual graph to apply more flow, and every possible path on this residual graph would have at least one saturated edge. This does not, however, mean that it is an actual maximum flow. Right? We've seen this before where it's possible for me to find an augmenting path in my residual that then removes some other option, so I have to make a new residual that has a new option for me to find more flow. Does that make sense? Okay, so this is the core two ideas. And now let's look at a hypothetical situation and see why maybe this, or we'll talk about the Dinic's algorithm and how it applies to a certain example here. So we remember this example. We had our S node, then we had, I'll label them A and B just so we can talk about them. A and B. And we had T here. We had, let's say, capacity of 100 on each one of these. This is the example that we talked about previously in class. And then we had, in the center, a single edge with capacity 1. Okay? So we recall this, right? All right? So in this example, do you remember why, so Ford Fulkerson, why did Ford Fulkerson do badly at this one? Yeah. Yeah, so it was possible for Ford Fulkerson, since it chooses an arbitrary path, it uses DFS to just find any path, could hypothetically find this middle path, and then find this middle path again, and repeat like that, and only add one flow at a time, right? So we improved on this by allowing Edmund Karp, which will only take the shortest one, which in this example is pretty clear is just going to be these, but it has a more complicated worst case scenario, but you can see that it does better here. But if we look at this residual, what would happen if I ran BFS and I found every path from S to T here? So I found every path from S to T, yeah? Through BFS. If I found BFS, let's say yeah, okay, so I found all the paths with BFS, and then I did something. Do you have any idea what that something is? Sorry, it's not a very clear question. What we can do is if I have my list of all of my paths here, I can try to apply them all. So if I apply one, so let's say I apply this one here, SAT, then I apply that one and I max it out, then I can see if any other paths exist. So if I then find this path still exists, if it's still in the residual, little thing that you can prove to yourself, if I do my augmenting path and I have a different disjoint augmenting path in my residual, I can just apply it. It doesn't even need to be entirely disjoint, by the way, it just needs to still exist. If I were to remove whatever saturated edges there are. Right? So it turns out by doing that, I am able to realize that there are situations where I can take multiple paths at the same time. So where previously applying one path at a time, I can just have, I apply this first one, let's say, with Edmund Karp, and then I make a new residual graph, and then I realize that I can take this one now. Instead of creating this new residual graph, instead of doing this extra iteration, I can say, oh, I can do this one, and I can do this one. So the core idea behind Dinic's algorithm is that what we're going to do is we're going to create a layered network. This is going to be useful for proving, although I'm not going to go very deep into the theory for this one just because it's a little bit more nitty-gritty. I did put a bunch of resources online, though, if you'd like to read proofs on this. And I do have some notes on the proof that maybe we can talk about if people are interested. So we're going to create a layered network version of the residual. And then from this layered network, we're going to find a blocking flow, or a maximal flow. Maximal flow. And the way that we can do this, the way that we can find a maximal flow, a way that we could do this, is we could run DFS, find all of the paths from S to T, and then we can apply as many as we can in an arbitrary order. And it'll turn out that this will give us a blocking path. Yeah? Yes, I can. So the core idea of what we're doing is, one, you're going to create a residual graph. In practice, in the actual implementation, we're not going to create a residual. It's just a conceptual thing, but for us, we're going to create a residual graph. So we're going to create a residual R. We're going to make a layered version of it. L, okay? Then we're going to find a blocking path, a blocking flow. So this step is maybe a little bit less obvious how we might do that. And in fact, there are modifications on this algorithm on how we do this step. So this step is going to be ambiguous for us at first, but I'll say one way that we could do it. Blocking flow in L. So we're going to just use L to do this. This is going to allow us to do our search for blocking flows a little bit more easily, and it will turn out that if there exists a blocking flow, there exists one in L, and that will be enough for us. We can just repeatedly do a blocking flow. So we're going to find a blocking flow in L, and the way that we're going to end up doing that, to start the original version of Dinic's, we're just going to, I guess the most simple version of this, I'll give you the most simple version of this, we're going to run DFS. We're just going to run DFS multiple times, and every time we run it, we'll find some path from S to T in this layered residual. We will add that to our augmentation. So I'll say repeatedly. So this is the simplest way to do it. You can repeatedly run DFS, add the. Then we can add the augmentation that it finds to some augmentation like list that we keep. Add augmentation to our, I'll call it to our blocking flow. And remove any saturated edges from our residual and repeat until DFS fails. Okay, does that make sense? So I'm saying we have our residual, right? We're going to make a layered version of it, removing any backwards edges essentially. Then we're going to run DFS on it, find some path from S to T. We're going to take that as our augmentation in our residual, and we're just going to remove any saturated edges and like basically decrease the weight along the entire path. And then we're going to run DFS again. As long as there's a path, we'll continue to do that. And then once we have our full list of these augmentations, that is our blocking flow. Does that make sense? Okay. If you aren't understanding this, please ask a question. You're going to have to implement this, so it's really worth understanding this one. Yeah. So maximal flow will not be a maximum flow. In fact,
in this case, though.
So not in this case. So there's no guarantee that a maximal flow is a maximum flow. The difference in general, by the way, by maximal and maximum is maximal, or maximal like this, is like a local maximum. But the maximum is a global maximum. Sorry, I need some water. Yeah, 1 second, sorry. Something got in my throat. Yeah, what's up? What? To construct a layered network, we could do BFS. We can do several things. But yeah. If we wanted to, we could. Basically, run a BFS, and then anytime you would repeat a node, don't. Like, don't add that edge. Yeah.
Okay, I think like the layers.
Yeah, it's a distance from us.
Like a layer network can only have edge.
Layered network only has those. Yes.
And then the blocking / maximal.
It is a flow assignment such that all of our normal flow constraints are met. You know, we have equal flow in and out, and every path from S to T has in our layered network is how we're going to be doing it. But in some network that we give it, we'll have at least one saturated edge.
So by
Yes. So the way that's like, it goes on. So like the way that this is going to work for us, so the reason why, if we had this in general, right, that would mean that there, so there still could be a path in the residual from S to T, that's why this is not maximum, if that makes sense. It sounds like it might be maximum, like if you just look at it, every possible path has a saturated edge, therefore there's no possible path, but that's not necessarily the case because there can exist paths that add flow and unsaturate certain edges. So it is actually possible for us to like, this isn't necessarily a maximum, it's just that we can't strictly add flow to get more flow. That make sense? Yeah. Same blocking. So not necessarily. We just need to find a blocking path. The guarantees for Dinics only require that we find a blocking flow. We don't necessarily need it to be a specific one. Yeah.
could you explain what you mean?
Yeah. So if I were to look at, like, for example, here, if I were to have something like this, like have this be 2, 1, 2, let's say. I might grab a different color. This marker's starting to fail me. And let me know if the color doesn't work, by the way. I have another blue one that I can grab out of my bag. So if I were to have something like this, like let's just, for a very trivial example, say that I have 2, 1, 2, 2, 1, 2. Something like that, right? Just arbitrary, not a particularly well thought out example, but just bear with me. I can find one path from S to T right here, right? And then I would say my augmentation, like my overall augmentation, I would say I have this, and I would have one along each one of these. So this is the flow that I'd be adding along here. Very similar to when we found augmenting paths, right? I just have flow along there that I'd add. Then I would, in the same graph, no longer consider this a viable edge. So this edge, I would basically remove one from each one of these. So this would be 1, this would be 1, this would be 0, and then I search again. I continue like this. So this is essentially repeatedly finding augmenting paths while only increasing flow. That makes sense? So I'm not decreasing flow at all, I'm only increasing flow. Although after I do iterations of this, because I will loop this, I can have backwards edges, but it's only pushing on things that exist in my layered network. That makes sense? Okay. So yeah. Essentially we're doing that naive thing that you might have thought of for maximum flow, just keep finding paths and adding them. And we showed, like in the discussion, that won't end up with an actual maximum flow, but it will end up with a blocking or maximal flow. The reason that I'm saying maximal flow, by the way, is just because this terminology is used in the book. I think a blocking flow puts a better image in your head of like, it's not, you can't keep pushing flow through this layer network. Anyway, so then the next one we'd add, so we'd have this, and then we would add this secondary path to it. So we'd end up with this full augmentation, which is all of the paths we found put together, like that. So when I'm saying adding, I'm sort of concatenating them together, although they can share edges, so they can actually be added together. Yeah.
Just to clarify,
No, it's not
there's
even
another step, there's more steps.
So I'm just saying this block right here is find a blocking flow.
Okay.
Finding a blocking flow does not find you the maximum. We
Yes.
proved that in the discussion. Yeah. So in fact, yeah.
So
So
those edges would end up being deleted.
So it is losing that information, but it's basically forcing us to find, it's intuitively it's forcing us to only find shortest paths, if that makes sense.
Disjointed ones,
What?
like they have to be
They won't necessarily have to be disjointed. They can overlap. Like I could have an edge like if I had another edge that went from here directly to T, for example, then that could exist in my graph. Although it would change the whole graph, but you get my point. I can have other sorts of edges here. No, but the point of it is so the point of it kind of comes down to the proving. If we like in our proving, we'll find that finding a blocking flow in a graph like this, there will always be a blocking flow in this graph if there's a blocking flow in the original graph. In our algorithm, we just need to repeatedly find blocking flows. So we will do this construction because it will save us runtime. Is the sort of the short answer why we bother with a layered network. We could just not. We could just have a regular thing, find a blocking flow and repeatedly do it, and that would give us a viable thing. But by doing the layered network, we actually save some time. Yeah.
Will you have an example of like
So I will a little bit. I also haven't finished the algorithm yet. So we're just stuck at so far at finding the blocking flow, which is the hard part of the algorithm, by the way. Yeah, but just to be clear, this isn't the full algorithm yet. Yeah.
So how can you
Yeah, so this is the layered residual, like this thing right here. This isn't the actual flow network. But like when I find, like I went through this process, I found these edges, and then I found this augmenting path, this blocking flow, which is sort of a more than just one path, but is a full blocking flow. Then I can apply this to my graph. So then I would, add one here, etc. To all the edges that I found here. And then I would construct a new layered residual. So I would this residual will be different, and I would construct a new one. That make sense? Somewhat uncomplicatedly, I think. So hopefully everyone understands this finding blocking flows here. I'm just going to repeatedly find paths and add them to my augmenting flow, and then all I have to do is apply them. So apply my augmenting flow. Aug/blocking flow, I'll call it. And then from 1. So this will just loop. So I will do this once. I've sort of skipped some implicit step here, which is if DFS cannot find a single path from S to T, then we have a maximum flow. So this will just keep looping until we have a maximum flow, and then it will exit. And it turns out that this does actually work. If you have questions of why this would work, that's a totally fair question. There are some little things here that are not 100% obvious. Yeah. Anyone have any questions on this? Yeah. Yeah. So blocking flow. So in general, do you understand what a blocking flow is?
Yeah, I know what it is, but when you do that.
Yeah, so all that we do to find a blocking flow, the easiest thing that we can do is take our graph. In this case, we're doing the layered residual, which that's comfortable too, what a layered residual is. Cool. And we just find paths, like an arbitrary path with DFS, let's say, find a path, and then similar to when we're doing our augmentation with the other residual algorithms, we find the minimum along that path, and we say that along that entire path, that is the flow change we're going to make, right? So that would be a single augmenting path. But the insight of Dinic is that we could, in fact, find another path also. As long as another path still exists in our residual after we remove that path from it, then we can apply that one also. So we can get a whole set of augmenting paths at the same time. And it turns out that if we keep doing this in our layered residual, we'll in fact get a blocking flow. And once we have our blocking flow, then we apply our entire blocking flow at once to our graph, and then we take another step and we get our residual from that. We construct our layered residual from that residual, and at that point we can check to see if we have a maximum flow, because there would be no path from S to T in our residual. So we do that check between 1 and 2 if we'd like to.
And what is residual on the algorithm?
So residual is the thing where every edge, which has some flow out of some capacity, becomes the 2 edges with a forward edge. It's every way that we can change our flow. So I could remove up to F flow if I have F flow forward, and I could add up to C minus F more flow forward. If this concept doesn't make very much sense to you, or if you don't recall all of this, you should rewatch the other lectures. I think on average people get this topic, so I'm not going to review it right now. But this image in your head is just every way we can alter the flow. And an augmenting path is some path we find in here from S to T that tells us how we could change our flow to increase it from S to T. Yeah, cool. Yeah.
So what is
Yeah, so a maximal point of a function could be a local maximum, whereas a maximum of a function is the absolute maximum, the global maximum. That's the terminology. That's used in a bunch of math fields. Here it just means that there is a thing where I can't add flow to it. Like I can't just push flow through this graph anymore because there is no possible path on here. We could, of course, apply this, make a new residual, and still add flow, but how it is, I can't push any more flow forward. It's just a terminology thing. Blocking, I think, makes more sense if we've pushed our flow in such a way that we cannot add any more flow without creating a new residual. Yeah?
How do we know that?
This is a good question. So it is non-obvious why we can just remove some of these edges. As a small insight, I'll say, will those edges ever appear in any of our layered residuals? An open question. So if I have a backwards edge, like in here, and I run my whole process, is there weight assignments I could give here, capacity assignments I could give here, such that these edges ever appear in my layered residual? I'll let you answer your own question. Yeah. Oh, not your question. Yeah, sorry.
We have the one arrow. If the bottom edge from S to 1 top one gets saturated first, then we never see it.
Yeah. So it is possible for them to show up. The insight here, there's one very important insight, and there's a more intuitive thing that you can see. It's basically as I saturate some of these edges, like for example, if I saturated this edge, then in the residual, in this residual, this won't be a forward connection anymore, right? So when I go to create my layered residual, this will be a layer 2 node, right? Because the shortest path to it in the residual will be 2 away. Does that make sense? So this edge still would come to exist in our layered residual. Does that make sense to people? Like, because of the augmentation we do, the distance from S, the minimum distance from S in our residual changes. In particular, if its shortest path has this new saturated edge, then its distance to that node must increase, in fact.
Is more or less enabling us to consider the
Yes, yeah. So I think you understand. Yeah. So this sort of tells us shortest paths in a way. It's not exactly giving us shortest paths. It has a relationship to shortest paths. But as we make augmentations to it, those shortest paths in our residual change. In fact, they tend to get longer. And in fact, they either get longer or stay the same. All of them do. Little thing that you can maybe think about yourself. And this means that generally these nodes will change their layer. So over time, these nodes will change which layer they're on, and eventually these new edges can come into play. They don't necessarily come into play, but they will come into play if every maximum flow has to use them. You can think about that also if you'd like. This is a little bit of a teaser of the way that we can do analysis of this algorithm, but I'm going to give you all, I'd like to give you a shot to do some analysis of this algorithm first, to see if you can come up with what the runtime for this is. Before I ask you guys to give it a shot though, I want to open it up to any more questions, and maybe if you feel like you need a hint, I'll give you another hint. Yeah. What? Is there a discussion Friday? No. Yeah, you're welcome to have a day off. Yeah, no, I've decided not to do discussion on Friday. Who wants discussion on Friday again? Pretty short, pretty small group. I'll give you guys a little problem to do on your own for some bonus stars if you want. Ping me on Piazza if I don't post anything tomorrow night, but I'll do it. But if I don't do discussion, then I get to have a Friday. Okay, cool. Anyone have any questions on this, or what I'm going to ask you to prove? What I'm going to ask you to prove is the full runtime of Dinic as described. As described, what is the runtime of this, and why? And I will give you the hint that the argument that I was just making verbally is going to matter for this. So I was making a verbal argument that these paths tend to get longer. There's a much more concise thing and a much more specific thing you can say that will help you find the runtime of this. Okay? Again, what you should probably aim for is calculating the number of iterations and the amount of work per iteration. That's a very good way to be able to calculate the runtimes for things like this. Okay, I'm gonna give you a little bit of time. I'll see how people are feeling after like 5-10 minutes. But go ahead and give it a try. It's the sort of thing I could ask you on a later midterm or maybe a final in terms of difficulty. This midterm is going to be slightly easier than this, though.
I would say that's also something.
Are we considering? Considering that we're getting the residual, or we have
Consider making the residual to be it's a comparison. It's not
So it only goes up, and then we're saying that the construction itself takes. So the amount of times you do the construction isn't necessarily the amount of times we create. Because if we're saying regardless of 1 and 2 both take E plus B. So I don't think the construction is also if we're separate path from this, the same that I hold, and then that one's and then you would only have to create this. And the fact that he's saying that the edges that can't stay in our idea doesn't encapsulate that makes it I'm not saying like what we're trying to do. I'm saying any sort of there's no way it's just E. There's no way it's just E times. So then you would have to be
And it's not much bigger.
I think
So the minimum one is the same as like the keyboard levels. If the minimum one is 2 all the way. Oh, maybe. So then we apply that from like adding a reset. And then. So it's basically the same as we're doing this. So it's like a single one. So bunch of augmenting paths can use the same to make it, I guess, max. Just for terminology. A blocking flow is a combination of paths. It's not a single beach path. So a blocking path is I mean, hypothetically, it can be a path that blocks, but a blocking flow. They can but they can't overflow.
that's why I think
So you find one augmenting path, another augmenting path, such that the don't overflow
like
like if this augmenting path has weight of 3, and this is weight of 2, it shares one edge. That edge has to have at least 5. Enough for this
But that's if you don't layer it out.
Alright, we're changing. So you don't change the path. Yes, yes. So you basically in your residual apply the first augmenting path. Like conceptually, you apply the first augmenting path one time, and then it will remove some edge, at least one edge, and it will reduce the capacity to be up. The like weight. Yeah, so in that case, it would be remove that edge, so I wouldn't be able to have the like, for example,
yeah.
hypothetically, in this case, here, then it is and then once you apply, as long as you apply this path, though, you still but then when you can't find any path, then you know that you have that's the layer. I think I know what I'm going to do. And then how to apply the layer. So I don't actually say until it fails anymore. So what I was saying is, as between 1 and 2, if I find a residual such that there's no path, then I return and I say I found that one.
I'm getting more. As I remember, but what about? Yeah, I'm asking.
So now it's going to expand.
I have them all.
Yeah, I think that's
Okay, anyone got any ideas real quick? Here, yeah. Hey, give me your idea.
For the runtime or the
For the runtime.
V squared E?
So, guess is v squared e. Yeah. V squared e is your guess. Who else thinks it's v squared e? Okay, cool. Good guesses. So that is in fact it. That is in fact the runtime. By the way, randomly guessing the runtime is a meaningless thing, but well, congratulations. Now justification. This is the part that matters.
Okay, so I was thinking because of the way that we're finding our paths,
Mhm.
the path must grow each time. And so the worst case path will run through every node.
Okay.
And then, the amount of paths we're adding per layer can also on DFS is order E.
Okay, so I'll label your thing. So this here is order E. Cool. We're all happy with that, I'm sure. Cool.
And then we're running a DFS at most V times.
So why at most v times?
That is where my logic falls apart.
Okay, so this one, yeah, Utkarsh is excited to say because he told me this earlier. Yeah.
Number of paths from the source to the sink.
Yeah. So the worst case for number of paths ends up being O of v, which is not true in a general graph, but is true in a layered graph, which you might have not realized. But you could have other paths that overlap and that you could reuse edges, you can reuse vertices, but in a layered graph, we won't. So this will in fact be O of v number of paths that will augment. We can justify this through some logic. I'm not going to do the full theory today because we have a whole nother topic I want to talk about, but you can in fact justify that. So that gives every iteration of this is going to be VE time. Oh, look at us. So we're actually increasing the amount of work per iteration, but how many iterations are there going to be? Your justification is hand wavy correct, I'll say. But I'll give you a more specific thing, unless anyone else has any idea as to how we can justify that the number of iterations is O of v. How can we justify that? Yeah.
In the example, the path was just one.
Yeah, okay. So I think this is actually a step towards a little bit of formality of this, although it's a little bit shaky on the formality, but I think your brain's in the right spot. So somewhat similarly, you want to give it a go?
I just wanted to say,
Yeah, so the maximum number of layers is in fact v. I think that should be pretty justifiable for everyone. The longest possible path, the longest possible non-cycle path is length v. That should be fine. What?
It's V because it's
Yeah, exactly. So yeah, the longest it could be is one, because we're never going to have any cycles in this, the way I constructed it. Yes, but how do we, like, so you sort of put these ideas together, add a little bit of formality, shake it up, and maybe you get there. Yeah?
Is it that once
Okay. Yeah. This is just about there. But you're saying this for every node? Are you saying it for any particular node? Like you're sort of saying that the layer that it's in increases, right? The shortest path, the shortest length. Okay.
The sink increases.
So this is in fact the case, and this is the argument that we are going to make, and the post I made on Piazza has one of the proofs of this, and that is the line of logic that they use, is that in fact we can show that doing this, applying a blocking path and then finding a new residual will necessarily increase the layer that the sink is in. It will strictly increase it. So it will increase by at least 1 every time we do this process, unless we find a maximum flow. So either we'll find a maximum flow or the sink will go at least 1 layer further, which I'm going to leave as an open logic puzzle for you of why that is the case. It's actually somewhat more complicated than what the intuition makes it sound like, but it is in fact the case that the sink will move at most V, it'll be at most layer V, which is nearly enough to prove this, but then we have to show that once it's at layer V, finding a blocking flow will be the maximum flow. Applying that will give us a maximum flow, which I will also leave as a little bit of an open question for all of you to think about. Perhaps I'll give it to you on a later test or something like that, so cool, maybe try it out. But in fact, it will be the case. So for one, every time I do this process, the layer that T is in will increase strictly. It'll at least become 1 greater than it was before. The greatest layer it could be at is V. And once it's at V, if I find a blocking path and apply it, I will have a maximum flow. So that is all of the things. Okay? So once I have all those together, that in fact gives me that this will run at most V times. So the number of iterations, I was tricking you all before, it does in fact decrease the number of iterations by increasing the amount of work per iteration. You could argue that it has like a nested iteration, whatever, but just to point out, the basic idea behind Dinic is in fact this, is that every one of my residual graphs, I want to do more work per residual graph. I want to find more augmentation I can make, and then sure, I can do more iterations, like I need to perhaps find more residuals, but or no, I need fewer iterations then, but I have to do more work per iteration to find all of that. Okay? All right. So, who thinks that this now V squared E is the best we can do? The answer could totally be yes here, by the way. I know that everyone thinks that I'm saying no because we're going to talk about new things, but who thinks that this is going to be the best answer that we can get? Perhaps even provably the optimal answer. Anyone? Raise your hand if you're brave. Okay, cool. So you're brave. Do you also think that this is the optimal? Okay. This Dinic, very good. There are a lot of different modifications we can make to this. But the important thing of this is not necessarily that we have this runtime increase, this asymptotic runtime increase, which is all well and good. But in fact, what we've looked at, this worst case scenario where we have to go through all these iterations, is a very unlikely situation in practice. And it turns out that in practice, the real like wall clock time, which is a thing we should care about perhaps more, is in fact significantly better than Edmund Curve. So it turns out that while we have this one little change from VE squared to V squared E, great, that's all well and good. But it turns out that in practice, this would be orders of magnitude different. This would take 1,000 seconds for something that would take 1 second here. So in terms of actual like physical runtime, say if you want to do something like image segmentation, it'll be a night and day. It'll be night and day how well these work. Okay? Cool. So again, there's a reason that this is the competitive programming answer to this problem, although it is, sorry for the spoiler, not in fact the optimal asymptotic runtime that we could get, or even the best empirical result we can get. But it is a very famous and good and relatively simple algorithm. Okay, so now let's talk about a class of algorithms to solve max flow. I think we have not that much time, so I'm going to be somewhat quick with it. If you want more on this topic, by the way, this is the thing that you need to know for your project. If you just got this and the next thing I'm about to say doesn't really make sense, it's fine. This is the important one. If you want more extension, because I don't have time to go through this as thoroughly as I want to, I posted a bunch of resources on Piazza that are like real research papers on topics like this, and you can see what modern research on this looks like, because this is open research, actually. I was surprised to find that there are papers being published right now improving on these asymptotic bounds, which is pretty cool. Anyway, so the other, I think I'll just do it up here. The other type of algorithm that we use for maximum flow that has very good asymptotics and empirical runtime, real wall clock time, I mean, are called push-relabel algorithms. Has anyone heard of those? I assume not. You have? Cool. Do you know anything about them?
No, I just read about them. They're used a lot because they're.
Yep. So they are used in practice. Although Dinic is also used in practice, depending on what your application is. By the way, little side note: Dinic on bipartite graphs is very good. You can think about why that is. I'm going to leave that to the people who are excited to think about this stuff. But it gets significantly better. The runtime is significantly better on bipartite graphs. Lastly, so we have the push-relabel type algorithms. I'm going to call one of these algorithms push-relabel as sort of the default one, but we can improve on this result with other modifications. Relabel. And this algorithm works like so. What we're going to do is we're going to have each of our nodes, we have whatever our graph is, something like this, etc., etc. Let's have this go directly to T, just because. Something like that. All right, so we have that with all of our capacities along here. And what we're going to do is we're going to assign each one of these a label. The label for S is going to be V. And for everything else, it's going to be 0. The intuition behind this algorithm is we consider a real-life system where each of these is at a certain height. So the source, you can think like a waterfall, perhaps an infinite source, an infinite stream at some very high point. In fact, V is going to be the highest height anything can be. And then it will flow only down. Okay? So what we're going to do is we're going to have each of these capacities. So I'll say like this is C1, C2, whatever. Doesn't really matter. And since it's a waterfall and it has infinite flow, it's going to fill these up entirely. So this is going to give us a bit of a weird thing here, which is that these nodes are now going to be completely at capacity, even though it's very possible that that is not allowed in our flow network. And we're going to call this type of flow, where I have, I'm no longer obeying my normal constraint of flow in equals flow out, and instead I will only have flow in is greater than flow out, is my new constraint. I'm going to call that sort of flow a pre-flow. So if you ever heard the term pre-flow, that's what it is. It's the idea that I have flow where the input can be greater than the output, but all of the flows are bounded by capacity, and I can't have the other way around. I can't have the output be greater than the input. Okay? And sort of the intuition of this, if you wanted a mental image of this, the one that's used in the CLRS book is that each one of these has an internal reservoir also. It has a reservoir that it can put any excess into that, and then it can, for now, have 0 output flow. Okay? This is called a push step. So a push step, we will choose push step. We will maximally push out our flow. That'll be, for this node that is infinite, so I can just totally put these at capacity. For any other node, I will only be allowed to push out as much as the input. That makes sense? So we'll maximally push flow to lower height. Lower height neighbors. Okay? Neighbors. So this is the push step. Is I'm going to choose some node that has input flow and has neighbors that are at lower height than itself, and I'm going to fully push them. So that's a step that I've done so far. Is I started with my source. It's the only one that I could do a push from because it's the only one that has neighbors that are lower height than itself. And then I just push as much as I can to my neighbors. Yeah?
Is it height? You just mean distance, right?
No. So that would be a different thing, the layer or whatever. Height is the label that I've given every node. So the height of S at this point is V, and the height of everything else is 0. So its neighbors are at height 0, so that means it can flow that direction. Now, if there are no viable options for pushing, what I can do instead is I can relabel. That's why it's called push-relabel. For relabeling, anyone have any guess what I can do? Yeah, but how do I do it? Yeah?
And then I'll
So what we're going to do is we're going to choose an imbalanced node. That is, it has more flow in than out. An imbalanced node. Imbalanced node. And raise its height by 1. Okay? Okay? And this is going to be, so to relabel, for example, I would go here and I'd say this one is now, since it's imbalanced, these two are imbalanced at this point, and raise it to 1. Now, since it has this capacity, let's say that C1, let's make these actual numbers so I can give you an example here. Let's say that this is 5 and 5, and this is like 2, 2. Sure, why not? 2, 2. And let's say that this has a capacity of 3, and this has a capacity of 3. Okay, something like this. Now, let's say I chose this one, I increased its height. Now it has 2 options. It can put flow this direction, or it can put flow this direction, right? So what it'll do is we will give an ordering to all the edges. Internally, we will have to do that. But I'll say that this edge comes first, let's say. So this one's going to become a 3. So I'm going to push as much as I can there, and then I'm going to push as much as I can here. Okay? All right. So this makes sense. I'm seeing some looks of maybe confusion. Yeah.
Is it arbitrary?
Which edge we pick first? Well, yes. So any ordering is okay, but we need a consistent ordering actually, because what we're going to end up doing is we're going to be undoing these once we fully push. So the process of this is we're going to do our full pushing as much as we can and relabeling. So the actual algorithm is okay. Basically, we will eventually be able to, once this becomes v plus 1, we send back our excess flow, and then the algorithm ends. Does that make sense? Yeah, okay. You had a question over there, by the way?
Yeah, so I was
So height means, so this is, the reason it's called height at all is that it's a real world analog. Like if I have two water flasks contained with a little tube between them, right, at the same height, it won't flow between them. If I raise one up, the water will now flow down to the lower one. That make sense? So it's the same sort of concept. As I raise the height, it will only flow to lower heights. Okay? Yeah?
Is the height always going to be 0 and 1?
What?
Is the height always going to be 0 and 1?
No, this could eventually become 2. In fact, they'll increase. They'll increase. Yeah. Cool. Yeah, so the way that this algorithm is run is we're actually just going to repeat arbitrarily either push or relabel, whichever one is allowed, as long as we can do one of them. We will just alternate doing that. We don't need to alternate even. We can randomly choose one of these two to do repeatedly as long as it's a viable operation until the flow is maximized. Until we get a maximum flow. And in fact, this does work. Anyone want to give a guess at what the runtime of this is? So the way I've described it. Yeah. V squared, anyone else? Any other guesses? V squared would be amazing runtime, by the way. VE, okay? VE, okay, yeah, sorry. So it in fact is O V squared E. No improvement, no improvement. Slightly more conceptually simple, and you can work out the runtime here. The problem with this is that by choosing this arbitrarily choosing these, I open myself up to a really bad worst case. Basically, I can allow myself to have to do this operation on every single node. I can have to increase my height all the way up to V for every single node, which takes a long time. But there are ways that we can redesign this that are better. So in fact, by only allowing myself to go this direction, so there's, if you want to look, relabel to front is a different algorithm that's in the CLRS book that you can find online. It turns out by doing this more systematically, where I do a full push sequence, and then I do a full balance sequence, which is essentially raising heights, it turns out by doing that, I can get this number all the way down to O of V cubed. Very nice runtime. We like that runtime a lot. Which is basically equivalent to V, by the way, which is what you guys were talking about. So it is in fact possible to do that. And fun little fact, by the way, there is another mathematician who made an improvement on Dinic that also gave it O of V cubed. So in fact, both of these algorithms, with some modifications, some clever management, we can actually get them both to V cubed. And it turns out, by the way, I just did some modern flow research. You can read the papers that I post on Piazza. I'll answer in a second. I just want to finish my thing. Papers I post on Piazza, there are in fact new results on this as of so 2019. I think an MIT group came up with an algorithm based on Push-Relabel that I believe is slightly more than V squared. So it's actually getting pretty close to V squared, which I told you is an amazing runtime. It is a very amazing runtime. And there's also some results that give us things like V squared plus O1. There's a lot of weird results in asymptotic research. You'll see lots of stuff like that. In my papers, they look horrible. You get terrible expressions. But this term we can bound depending on certain actual inputs. Like we can say for certain graphs this number is low, stuff like that. By the way, I'll throw out just this number. I think I may give this as a bonus at some point for someone to prove, but I'll give this to you. On bipartite graphs, like I was saying, Dinic actually is provably O of square root of V times E, which is a really nice runtime. So there's lots of stuff you can do. And flow is a surprisingly active area of research. So you can find some modern papers talking about this. This is how any field looks like when you start getting to the modern front, by the way, if they're still active, and start branching into a whole bunch of different techniques that have different trade-offs. Yeah, but the heart of it, I think the only things that are really, really important for you guys to walk away from is understanding Ford Fulkerson, really understanding residuals, that is, then understanding, and augmenting paths, then understanding Edmund Karp and why it's better, and how to do that sort of proof. And then Dinic is really the one you need to know. If you want to know Push-Relabel, it's a good thing to know because it is sort of the modern frontier. The very best modern results use Push-Relabel. A lot of algorithms that you would run on whatever, like OpenCV or something like that, would use something like Push-Relabel most likely. But Dinic is a good algorithm to know and is sufficient for your homework. For your project, you'll just have to figure out how to implement it, which is going to be a lot of fun for all of you, I suspect. Yeah. You're saying this. So when you're referencing it in, when you're referencing on on a project, or if you're referencing on an exam, perhaps this one. Unless you are confident in your ability to explain V cubed, then don't use it. Yeah. And that's in general, you should only use things that you're very confident in. Yeah. Why is this better than this? Because E in the worst case is V squared, and in the best case is V. So this is considered better, even though in a very sparse graph they're equivalent. Yeah. Yeah. It's a dense graph. We can consider E to be V squared. If you want to replace all of those, that's like the worst case scenario in all of them. Cool. All right. Anything else? I think it's pretty close to time. If anyone has any questions on the exam, also now would be a good time. Yeah.
Where is it?
Where's the exam? I believe it's S110. It's posted on Piazza, which is just a room right down the hall. I don't know why they moved us even, but I think we're down the hall. Yeah. Starts at 7 p.m. tomorrow. Don't miss it. Anything else? Any other questions on the exam? Okay. Well, I'll see you all tomorrow. Goodbye.
doing the homework because my PC died today.
Okay.
And hopefully I'll be able to fix it. But I don't know.
Okay. Okay. Well, best of luck with that. Yeah, you can request an extension. For the first written, we just want you to submit something. But if you have something like that, it's okay. We'll give you like a day or two. You can do Push-Relabel if you want. Dinic is just slightly more intuitive, I think. Whichever one you're okay with is fine. Yeah. Yeah. I think there's also Dinic is easier for you to implement in such a way that isn't terrible, that is actually that runtime. Push-Relabel, it's more likely that you fuck it up and it ends up in a really bad runtime. That's my gut. I've never implemented them actually, so I don't know for sure, but that's my gut feeling. I probably will. Yeah. No problem.
How do you convert the problem that was on the exam into a flow problem? Like I've used ChatGPT and I still can't figure it out.
That's good to hear. That's good to hear because I want them to not be cheatable. I think I'll discuss. I know the makeup's done and all of that, but I will discuss later because there is some similarity to stuff on the main exam. It's not one-to-one, but you know what I mean. Yeah.
So I have a question about the cheat sheet. I thought last class you said it could be printed, but on the other you said it
The real truth of it is I don't care.
Okay. No,
I just don't want people like asking ChatGPT to make them a cheat sheet. I want people to make a cheat sheet themselves because that's an act of studying. Yeah. So do that. Yeah. I'll look at yours. If it reads like ChatGPT, then I'll fail you or something. All right. Yeah. Yeah.
The header for like project. It sounds like if you were close to someone, you should like put them in the corner.
Yeah.
We do that just like as a small aside, like no Wikipedia.
Yeah, it's fine. It's fine. It's one of those things where if we will look through the assignments. If there's any that are super similar, we're gonna flag it, and then we'll be like, you know. We'll maybe make an accusation if we think it's really bad, but if you say you collaborated, it's basically just like getting in front of it and being like we know ours are similar, but like we're being upfront of it, and it just will make us softer if we have to do anything about it. That's all.
For the grading of the written portion of the specifically the algorithm like pseudocode portion.
Yeah.
Is that like do you take into account like the actual like tests that are done in the programming portion at all? When you
No. So they're graded disjointly as much as I can. So just what's on your written is graded on the written and vice versa. But we will care about like if you have really bad runtime of your algorithm, we'll care about that still. And if your algorithm is incorrect, we'll care about that too. If they don't match, we've already checked and we know a bunch of people's don't match. We're choosing to overlook that for now, but know that might change in the future. Yeah.
And then when you're looking at the algorithm, is it like do you just like look at it face value, or do you like try to like implement it yourself? Like,
I mean, we don't try to implement it, but we can read pseudocode well enough to know what your algorithm's doing. Yeah. No, we have RTA. We'll actually just read through the whole thing and figure out what your algorithm does and decide if it's correct or not. Yeah.
Write them down.
I just quickly a question. Which of the items, the next or Push-Relabel do you prefer?
Do I prefer? I don't have a strong preference. To be honest, I had to learn these for this lecture. So, from what you can probably tell from the way that I spent much more time on Dinic that I preferred talking about it. I think it's a little bit more intuitive, but Push-Relabel, from the little bit that I read of the papers that I posted, seems to be better for runtime and better for guarantees of your algorithm. So, I think Dinic is cute, and I also you can see this if you look at the Piazza thing. There's a little description of the algorithm written by an MIT professor of some sort that wrote up like typewritered it. So it's an old thing. It's 1970s, and it is pretty cute to have something like that. I don't know. So it's more historic than Push-Relabel is. Push-Relabel also is very there is actually connective tissue between the two of them, surprisingly. So you can modify Dinic in a way that it starts becoming Push-Relabel. Yeah. So anyway.
Do you care for runtime for tomorrow? Like,
I mean, I care about it.
Does it change the grade?
If it's really bad, it does. Basically, there'll be a threshold that's acceptable for all the problems. That I'm not going to tell you ahead of time, but it should be good.
You can't be like, oh, and